Hello everyone, this is FTC Team 9511 Low Voltage and welcome to this tutorial on the first step of tuning Roadrunner. So first off, let's head to the GitHub for the Roadrunner Quick Start and copy this link and head on to Android Studio and create a new project from version control. And once we have that open, we can head on to the team code Java drive and drive constants class and start our tuning. So first off, an important thing that we need to decide is whether we're using drive encoders or not. This basically depends on if you have odometry or any external encoders on your robot. Since this video is being made during the Freight Frenzy season in which a majority of teams are choosing not to use odometry, the answer for this will be yes. And let's head on to the drive constants page. Alright, so the first step is defining our ticks per revolution. Learn Roadrunner has provided a lot of specs for these specific motors. Our chassis for this season uses 4 GoBuilda 5203 series motors, and if you head over to the specs for that, we can see that our ticks per revolution is this value. And then while we're there, we can also copy over the max RPM, which is 312. Okay. So next we have a run using encoder and motor velocity PID. What this basically means is if your run using encoder is true, you are using drive encoders, which for us is true. And we are going to be tuning the PIDF coefficients later in a later step of Roadrunner. So our robot this year uses 96mm mechanism wheels, and when you're defining the radius for Roadrunner, there's two things that you need to be aware of. First of all, it's asking for the radius and not the diameter, which is what a lot of wheels go by from the manufacturers. And also, they ask for it in inches. So when you take the 48 from 96mm as the radius, you have to convert it to inches, which is 1.889 for our wheels. Okay. Now gear ratio. So our motor gearing looks like this, where we have our GoBuilda motor and then two gears that switch the axial rotation and then the wheel. So what gear ratio looks for is whether the output shaft of the motor spins at the same speed as the wheel. And although we have a lot of internal gearing on our drive motor, this is a 1-to-1 gearing ratio, so we can leave this as 1. And finally, in the step, we have track width, which is essentially just the distance in inches from the middle of one of your left wheels to the middle of one of your right wheels. And for our robot, this is 11.25 inches. Okay. So for now, we can leave this step alone because if applicable, we use this in a later step. And base constraints is the same because all of these are going to be empirically tuned in the later steps. Okay, so now we have a step where we need to open sample mecanum drive. So here we basically just match up the hardware IDs of the motors in Roadrunner to our configuration. So I know for our robot and a lot of teams, instead of using left front, we actually just use FL, and for this we do BL. So whatever your team chooses to use, that's what you put here. Okay. And finally, we have the IMU velocity stage. So you only need to change this if your control hub is mounted on a different axis than the default. So this is what our robot looks like, which essentially has both hubs mounted vertically, which means the default axis of Z is good enough. So if your control hubs are mounted flat on your robot, as in parallel to the floor, or anything like that, you're going to have to change this to a different axis. And lastly, we are going to need to reverse our motors if applicable. So different robots have different motor setup configurations. So this really just depends on your chassis and how your motors are mounted. But basically, when you get on to further steps and when you run straight test or any other steps where your robot is supposed to move forward, if it doesn't move forward, that means you have to debug your motor direction reverse.